you do that for yourself, or is that something like you're working on?
For what?
Your videos.
Oh, it's for you guys.
Can you put it back on the internet?
It's on YouTube, yeah. It's just something you can go back and look at if you need to.
Very nice.
Yeah.
That takes a lot of time, doing a lot of editing and stuff.
I don't do any editing.
You just cut it and put it in?
I just, yep, it's a direct.
Do you use a program? What do you use?
Well, I don't edit.
Anything you just put it as a window video?
It's a MP4, so it goes right up. So if I cuss or get on anyone, it's on there. Yep. Okay, let's get down to business. Homework, y'all do okay with that? I had 33 views on the homework video, which is pretty good. We're going to go to a new chapter, chapter 7. Title of chapter 7 is trig functions. So chapter 7, trigonometric functions. We're going to have to build up to that. We're going to start out 7.1 talking about angles and their measure. All right, so most of us are familiar with the concept of an angle, right? I mean, it's probably from grade school you have some idea of an angle. But let's just make sure we get some terminology in place, some language before we proceed. So let's start with this idea of a ray. Okay, and I'm going to just be purely geometric here. I'm not going to write all the definitions down. They're in the book. But when we talk about a ray, it's a point and then all the points in a straight line in some direction forever. Right? That's what a ray is. It's not a line. A line goes both directions forever. It's not a line segment. A line segment starts somewhere, stops somewhere. So that's a ray. And then this point right here, we call the vertex of that ray. And when we talk about angles, what we have are, the idea is that you have two rays, and they share the same vertex. So if you have one vertex, then you have a ray, then you have some other ray that shares the same vertex, then we can somehow quantify or talk about this space between them, and that is our angle, right? This is the angle. So this right here, we'll call this theta. That's the standard letter we use when we introduce the idea of angles. That's a Greek letter. And this ray right here on the bottom, we call this the initial side of the angle. And then this one right here would be the terminal side. So we imagine taking this ray, and you can almost imagine just rotating it through and stopping. So it looks like two rays, but you could imagine just taking that ray and then turning it, right? Now, there's another way that we could have got to that terminal side. We could have rotated this ray counterclockwise, right? Which would have gone like this. Or we could have got to that terminal side by rotating clockwise around, right? So there's two different ways. This way would be clockwise. And then anytime we rotate clockwise, we say that's positive angle. And then whenever we rotate the other direction, right, this is counterclockwise, and that's a negative angle. Now, we just all came to an agreement that positive would be clockwise. What, did I just mess this up? Yes. I did. Thank you. Sorry. My brain is elsewhere right now. Okay. counter. Y'all just let me know if I say something completely stupid like that. Okay? Counterclockwise is a positive angle. Clockwise is negative. We could have, when we were establishing the idea of angles, could have done it the other way. We could have said that this was positive and this was negative, but this is the way we've agreed. All right? Now, this angle, where's my little, there it is. This angle, when we try and throw an angle onto our flat sheet of paper, which it's on a flat sheet of paper right now, but in general it can be out in three-dimensional space. So when we place this onto a flat sheet of paper, we place it onto what we call the Cartesian plane. Have you all ever heard that before? The Cartesian plane? Okay, so all of our geometry, all the geometry that we deal with in calculus, until you get to Cal 3, well, sometimes in Cal 2, you do talk about polar coordinates. So pretty much in through Cal 1 at least, you're going to be, everything you do geometrically is in the Cartesian plane. So the geometry in the Cartesian plane is the stuff that you've grown up learning, like parallel lines don't intersect. The sum of the angles of a triangle is 180 degrees. Things like that. That's all part of Cartesian geometry. But that's not the only geometry there is. There's other types of geometry. So when we say Cartesian, we're all kind of agreeing that we live in a certain type of world with certain rules. Now in the Cartesian plane, normally we label this our x-axis, our y-axis, right? And our standard, like the standard that we use when we talk about angles, is we have our initial side of our angle always pointing out from the origin out the x-axis. That's the standard. So if we start our initial side of our angle here, and then draw that out or swing through some angle to our terminal side, this angle right here is in what's called standard position. Right? This is what we call standard position. Again, this is just so that we're all kind of on the same page, all right, when it comes to like agreeing where this angle is. If we all start to draw things in standard position, then the angle, a certain angle here, will look the same for you and me, right? As opposed to if we rotate it around. Everything here pretty okay so far? Okay, now in the Cartesian plane, we have naturally 4 separate sections of the Cartesian plane. And right, it's broken up by the x and y axes. And when we start dealing with angles, we want to have some labeling or some name for these 4 regions. So we call them quadrants, quad for 4. So this is quadrant 1. Let's say quad 1. Here I'm just going to put Q2, Q3, excuse me, and then Q4. And you know what? I'm just going to call this Q1. Now, can anyone help me understand why it is we went in that order? Why we went like 1, 2, 3, 4 instead of like 1, 2, 3, 4?
Positive.
Go ahead. Yeah.
It's all positive and top row.
What's all? What do you mean?
Positive, positive, and then you get to the half positive. That's where you want to start.
What's positive, positive?
Y and X.
So y and x is positive, positive here.
Yes.
So I should call this quadrant 1, and then here. Why? What's your reasoning?
Well, then you just start that, and then you want to go keep it sequential. That's just what I was told in high school.
You're on the right track, but the way you're saying it is not. Hold on, I saw a hand here. Yes?
Can we use the unit circle, like the way that the angles are?
Uh-huh.
Start off with a positive angle on this side, and then you go around.
Yeah.
60 degrees.
Exactly. I think you're going to say almost the same thing, or no? Go ahead. Go for it.
I was going to say, wasn't he left-handed? That's when he went that way?
Oh, like this?
Yeah.
Oh, I've never heard that one. Who's he? Oh, this Cartesian? Oh, okay. Actually, you can have the Cartesian plane without the idea of the geometry of this. The reason why we do it is because if we are going to say this is standard position, right? Pointing out the x-axis, and that a positive angle is what's going to happen as we start rotating counterclockwise, right? Then wouldn't it seem natural that you want to start out in the first quadrant and then slowly proceed through to the second quadrant and then to the third and then through the fourth? If you go 1, 2, 3, 4, then you're going to start out in the second quadrant, then the first, and then you're going to go down to the third, right? I mean, just, do we agree? So it just makes sense to go through this way. That's it. So those are our quadrants. Let me see, this section's kind of weird the way they present it, but I'll try and stick with their logic. All right, when it comes to angles, we haven't talked about how we measure them, right? So there are two standard ways we measure angles. What are they? Do you know? Degrees and radians. Okay, so let's get an idea of what this is all about. If I take this is a yardstick, I guess we call this, right? This has a certain length to it, and then it's broken up into these smaller pieces. And in this particular case, this looks like it's 36, it says 1, 2, 3, 4, 36 miles. What is that? Inches, right? 36 inches. So we take this and we break it up into smaller pieces, right? Inches is a way that we can measure this. That's not the only way we can measure it, right? We all agree on what 1 inch is, but then we also have other units of measure like meters. And meters and inches aren't the same thing. When it comes to angles, it's the same idea. We have two different ways of measuring. Degrees is one of them, radians is the other. Degrees is the one that makes most sense when compared to like a ruler. Because what we're going to do for degrees, and this is what we're going to start with, degrees, is we take the angle formed by rotating around 1 time. That means our initial side, we're going to start on our initial side, we're going to go around 1 time, and our terminal side is going to land right on top of our initial side again. Right? So that's like this measurement right there. So imagine that's some given length, right? Some given measurement. And what we do is we cut that into 360 equal pieces. Right? So the angle that goes all the way around like this, cut it into 360 equal pieces. So the angle formed by rotating around 1 time and then partitioning into 360 equal angles. Each of these has a measure of 1 degree. And we use that symbol right there, top right little O there, circle. That seems very natural, right? We said, hey, this is the distance all the way around. We just cut it up 360. Why did they do 360? Why not 100? I mean, why use the 360?
That makes you go around?
Yeah, but imagine no one had ever told you 360 before. All right, like if I just hand you this ruler and I say, go ahead and cut it into equal segments. You get to choose how many you want, right? You could cut it right in half and have 2 equal segments. You could cut it into thirds and have 3 equal segments. You could have cut it into 10 pieces, right? So why 360? Actually, there's some historical reason why, but they could have used any number, right? Could have. Just like with 1 foot that used to be based off of the king in England's foot or something like that. The king would get out and be like, that's 1 foot, you know, and that's what everyone agreed upon. And then they decide to cut that into 12 pieces for inches, right? Why 12? Well, they could have used 10. So this is kind of arbitrary. It's kind of an arbitrary number. Now, it does turn out that 360 was thought out. I mean, it's a number that is highly divisible. There are a lot of numbers that divide into 360. So you can break it up into nice equal sections. Okay, everyone here familiar with the idea that the angle all the way around is 360 degrees? Okay. I realize this is not brand new information for you. Let's continue to talk about degrees then. What are the common angles?
90, 180, 360.
270.
Okay, so let's write them down here. We have the angle, of course, where your terminal side and your initial side are right on top of each other, like this, where there's no rotation at all, right? No rotation. So that would be 0 degrees. And then the next common one, I heard 90, yes?
Yes.
90 degrees, I'll do that one. Now, the reason it's 90 is because if the whole thing is 360, right, then a quarter of the rotation, because this is only 1/4 of the rotation, would be 1/4 of 360, which is 90. And then the next one, 180? Hold what? I'm going to leave this. Oh, you got? Okay, what about this one? Initial side, terminal side over here, that angle, 180. And then 270 would be pointed straight down?
Yes.
Okay. Can I erase? So initial side, terminal side, go around like that. And I should have put here this one right here, 90, like that. This would be 270 degrees. I mean, those are the most common ones because they just take your full rotation, cut it into 4 equal pieces, right? But there are more common ones, and we need to be familiar with them. And I'm going to go through them right now, all right? And I cannot stress to you enough how important it is that you catch on to the pattern that I'm about to show you. Maybe not so much now because most people are comfortable with degrees. But when it comes to radians, it's a little harder to catch on to. So, what about that angle right there? I'm going to leave it dotted for a reason. What's that angle right there?
45.
Looks like 45, right? Because what I've done is I'm splitting up 360 into 1, 2, 3, 4, 5, 6, 7, 8 equal pieces, right? And if you take 360 and you divide it by 8, you should get 45. So each of those is, each one of these angle measures. That's 45, that's 45, that's 45, that's 45, right? Okay, so let's label the angles here. We've got 0 degrees here, 45 here, right? Now, I understand this is probably already hardwired in your brain, but think about this for a second. This is 0, right? This is 45. This one is what? 90, but I want you to understand that that's 2 times 45, right? It's 2 of these, right? 2 of the 45s. 2 times 45 is 90. I'm even going to put up here, 2 times 45 equals 90. Then this one should be 135, but I want you to understand that's 3 45s, right? 3 times 45 would be your 135. And then this one, of course, was 180, but that's 4 45s. Trust me, this will help later, all right? So that's equal to that. And then the next one should be 5 45s. And that should be, what, 225? And then I proceed, I'm almost to the end here. This is 6 45s, which is your 270. And then 7 45s, which is 315. And then lastly, if we come all the way around, that should be, what, 8 45s, which is 360. Good? All right. So what if I were asking you now to show me where negative 135 was? The angle negative 135. So positive angles is counterclockwise, and negative angles are clockwise. So all you'd have to do is what?
Start going that way.
Start going clockwise until I get to the equivalent of 135 degrees of rotation, which if I count by 45s, it's like negative 45, negative 90, right? Negative 135. So it'd be this right here. So if I asked you to show me negative 135, it would be that piece right there, right? Negative 135. It would be in quadrant 3, yes. Okay, that's that. Now let's proceed. Those aren't the only common degree angles you need to know. The next group, and this is actually the last group, are these were all, do you agree that all these angles were multiples of 45?
Yes.
Okay, this next group is all the multiples of 30. So I'm going to start out with 30, which should be less than 45. This would be 30 degrees. And then the next angle would be 2 of these, right? 2 of those should put you right here. This should be 60 degrees. And again, this is 2 times 30 degrees. The next one, 3 times 30, which would be 90. So this is what I'm trying to get you to see. I'm counting my way around. 30, right? That's 2 30s. That's 3 30s. The next one will be this one right here. 4 30s. What's that angle there? 120. The next one would be 5 30s, which that's 150. Then when I get to my 6th one, right? 6 30. 6 times 30 is 180. And then keep going. What is this? 210. The next one's here, 240. The next one, 270. And then 300. And 330. Okay. I know this is starting to look like a big jumbled mess. The biggest thing, the biggest takeaway is I don't want you to think about memorizing this as much as I want you to think about how to count it out. I think it's better, especially when we get to radians, that you can count your way around. All right, those are the common angles in degrees. Now, you know how when we have like this ruler, like we can break it down. You could have like yards, and then yards can be broken down into feet, and then feet can be broken down to inches, right? We have the same sort of thing when it comes to degrees. If you take 1 degree, you can break it into 60 pieces. Why 60? Someone wanted to use 60, all right? So imagine now, let's just act, even though this is not accurate, let's just act like this is 1 degree. I realize it's not that big, okay? It's actually really small in here, isn't it? 1 degree? But if we were to take that 1 degree and split it up into 60 smaller pieces, 60 partitions, then each of those would be 1/60th of a degree, right? This would be 1/60th of a degree, would be one of those little guys right there. We call this 1 minute. And we do almost, well, like single prime mark, 1 minute. So how many minutes are in a degree? There are 60 minutes in 1 degree. Make sense? That's just like me saying, how many inches are in a foot? You'd say 12, right? There are going to be 60 minutes in 1 degree. So this is 1 minute. And we can break that down even further. We can break it down to seconds. Why they use minutes and seconds? Again, that's the convention. But it is good that they're using 60, right? Because aren't there 60 seconds in a minute and 60 minutes in an hour? Yeah, yeah. Okay, so now take one of these and let's blow it up. Let's take that and kind of zoom in on that. If we have this, and this right here is 1 minute, and then we break that up into 60 equal pieces, 60 partitions. Then one of these is 1/60th of a what?
1 minute.
Of 1 minute.
Is that
Which-
how you take that?
Yes, this right here, this little prime mark is our minutes.
Oh, okay, you don't have to write the one.
You don't have to write 1 minute. That means 1 minute. This was me saying, like in quotes, 1 minute. That's how you'd say this. So this is, each one of these is 1/60th of a minute, which is actually called 1 second. Don't confuse my quotes with this, okay? How many seconds are in a minute?
I mean, 60.
60. How many seconds are in a degree?
60.
How many seconds are in a degree?
60 times 60.
60 times 60, right? Each of these minutes has 60 seconds in it. So there's 60, then another 60, then another 60. So how many total? 3,600. There are 3,600 seconds in 1 degree. Now the book summarizes this for you. So again, I mean, you can always go back to the book to reference, you know, nice little tables and charts. Yes?
Oh, never mind, excuse me. Cut off.
All right. What we want to do now is we want to just take a little bit of time converting, because sometimes someone will give you a degree measurement. They'll give it to you in what's called decimal form, and you want to convert it to degrees in minutes, or sometimes they'll give it to you in degrees in minutes, and you'll want to convert to a decimal. So let me illustrate that. So converting degrees from decimal form into degrees, minutes, seconds. I'm putting DMS there. That a lot of books use just DMS so that you understand degrees, minutes, seconds. All right, I'm not trying to be like super lazy. All right, degrees, minutes, seconds. We want to be able to convert from decimal form to degrees, minutes, seconds, and the other way around. So notice I put arrows going both directions. All right, let's practice. I'm going to give us an example. Let's start with a very easy one. Not easy, I shouldn't say easy. I should never say easy. Let's go 31.54 degrees. Now, is this one of our common angles? That is not one of our common angles, right? I would like to take this angle and convert it to degrees, minutes, seconds. So how many degrees for sure do we know we have here?
31.
There's 31 plus some change, right? So what I'm going to do first is I'm going to take 31, right, degrees, and then plus some change, right? Now, the change that I have here, I need to figure out what it is. This is 0.54, right, degrees. So off here on the side, what I want you to think about is what would 0.54 times, what number am I going to use here? I'm going to try, I've got degrees here, I want minutes. So give me a relationship between degrees and minutes. How many minutes are in 1 degree? There's 60. So think about it this way. If this was just 0.5, not 0.54, if it was just 0.5, wouldn't that be like half of a degree? And that would be 30 minutes. So to get that, what you're doing is you're taking the 0.5 and you're multiplying it times the 60. That's the same exact thing I'm going to do here. I'm going to take this 0.54 and I'm going to say multiply times 60, right? Minutes. Minutes. And tell me what you get there. So get your calculator out. What do you get? $32.4? 32.4 minutes, right? Okay. Does it make sense that it would be about 32.4 minutes? A little bit more than half of a degree should be a little bit more than 30 minutes, because a whole degree is 60 minutes, right? So does that 32.4 make sense to you? Okay, so I'm going to say here now, 32, you know what, I don't want the plus there. I'm just going to write next to it 32, don't put plus, minutes, right? I for sure have 32 minutes with some change, right? With some change, 0.4. So now I need to convert that 0.4 over to seconds. So how would I do that?
60.
Multiply it by 60 again. So I'm going to take 0.4 this time and multiply it by 60 seconds. And that will give me what? 24 seconds. Now, degrees, minutes, seconds is used here and there. It's not, you normally don't see degrees, minutes, seconds. But you'll be in some calculus class and they'll give you an angle in degrees, minutes, seconds, and you'll have to convert it or something. So this is just so we know how to do it. Everyone understand? Take your decimal, the whole number out front, that's your degrees. Take that, multiply times 60. Take the whole number there, put it as your minutes. Take the decimal, multiply by 60 again. Take that number, stick it here. If this number 24 would have turned out to be a decimal, we would have just put like 24.5 or something. Just put it in there. That's fine. All right, that's how you go from decimal form into degrees, minutes, seconds. So we just did decimal form into this. Let's try and go backwards. How do we go backwards? Let's take 30. Let's just take the same problem so we know what we need to get to. I think this one's a little bit easier to do, because all you do here is you say 31 degrees. This is where I was putting the plus. I should have put it on. I got the 2 backwards. Now, 32 minutes, I need to convert that to degrees. So how do I undo what I did earlier? I divide that by 60. So what? 32 divided by 60, right? And that'll be degrees. And then what about this next one? What do you think we do with the 24? Take the 24 and divide by, what do y'all think? 60? 120? 3,600? Let's do it. Let's try 60 and see what happens. Let's see if we're right. We know what the answer should be, right? 31.54? Let's try 60 in here and see if we get the right answer. So what's 32 divided by 60 on your calculator?
25.
Okay, it's 0.53333, whatever, repeated forever. All right. Plus, what's 24 divided by 60? 0.4. Okay. If you add those up, is it this? No. Something's off. So we're not going to divide by 60. We're actually going to divide by 3,600. But why? Think about what we did when we went from here to here. Didn't we multiply by 60?
Yes.
And then again by 60? So that means we have to divide by 60 twice, which means 3,600 here. I just wanted you to see why it happens. So this should be 3,600. And now can you do that on your calculator and tell me what you get?
0.006666.
0.00666. Scary. And if you put those together, you might have some rounding error, but this should be approximately 31.54 degrees. Is that fair? Okay.
Backwards is always more
Yeah, the going from degrees to degrees, minutes, seconds, take the decimal, hit it with 60, write down the integer, take any remaining decimal, hit it with 60 again, write down the integer. Going the other way, take 31, or whatever the degree is, plus whatever the minute is divided by 60, plus whatever the second is divided by 3,600. Yeah, fun stuff. I really don't like this stuff, but. All right, let's talk about the other way we like to measure angles, and that's a radian. And I've been excited about this for the last few days, talking about radians. Okay. Other way to measure angles. Radians. And what I really, really hope to do here is to help you understand what a radian is, right? Because I think if I say what's 1 degree, everyone has an idea that that's like a really small little angle. If I say 360 degrees, everyone has a like visual in their, in their head. You can understand what that means. 180 degrees, you can see it. But when I say 1 radian, that's a measurement of an angle. And I want you to understand what it is. Okay, so I have a visual. There it is. Okay. I have a little bit of a visual aid here. Okay. So I'm going to get a little line segment here, all right? I'm just going to stop somewhere arbitrarily, right there. And does anyone want to help me? You have to be on camera. All right, here we go. What you're going to do is you're just going to mark the points so I can hold this up. So I'm not going to let go of this so it doesn't change, right? So you're going to mark here first. Yeah, just above it or below it. Yeah, there, and then the end here. Okay, that's good. I'll take that. I'll call you back in a minute. I'm going to need you again. Okay, so I took that little segment right there, right? And then I'm going to connect this. And now what I'm going to do is I'm going to rotate this around, okay? And I'm going to do it in a different color. So if I rotate this around like this, oh wow, that didn't work. Okay? I've kind of drawn part of a circle, right? I'm going to take this same measurement, and now I'll need you again. And what we're going to try and do together is we're going to try and take this same measurement, we're going to try and wrap it around the circle. Okay, so you're going to have to help me out. I'm going to hold it here. You kind of, move it around there until we get, you see what I'm saying?
Yes.
Okay, so right in there, you think? We'll go a little bit, yeah. You see what I'm saying? What we're trying to do here?
You're measuring the
And
plane.
then mark that up there. Okay, good. All right, hang tight. Just
Hang tight.
stay right there.
Hang tight.
Okay, you see that right there? This measurement we're going to call R1. It's some radius, right? Agreed? And what we tried to do is I tried to mark it where the length right here was also R1. Do y'all agree with that? Yeah? Okay. I'm going to go with a different radius now. We'll go longer. So you're going to mark my 2 points. Go ahead and let's mark one out here. Okay. And yeah, that's good. Let me see the marker real quick. Try this out.
Let me try it.
I'm gonna draw my circle first. That should be all I need. Okay. And now you're gonna have to help me do this. This is gonna be tough, but we're gonna try and wrap this around the circle again. Okay. Here we go. That's really, yeah, that's kind of hard.
There we go.
Let's try that. Mark that up there. Okay. What do y'all think? Do y'all see what's about to happen?
This distance.
If I go from here up here, it's the same angle, isn't it? Isn't it? I mean, I've got some inaccuracy here because we're good. We're trying to use a string and it stretches, and he's not very good at wrapping things around in circles. No, you get the idea though, right? So if I do this one right here, and I go like that, and then I take it and I wrap it around, I'm going to get the same angle. And it works for any radius, any radius. So this angle is interesting, isn't it? Because if the radius of this, if you go out a certain radius and then you draw a circle and then march along that circle a distance that's equal to the radius, you form an angle, and that angle is always the same, no matter what your radius is. So why don't we, since it's so special, why don't we call it something? How about we call it 1 radian? That's 1 radian. That's what it is. 1 radian is the angle that's formed when you go out a radius of r, and the technical word is, and then subtend an arc of distance r. And that gives you 1 radian. So 2 radians would probably be, I don't know, this. 2 radians would probably be,
Easier to get the second material angle.
yeah, once we have, I'm trying to double this. I don't think I did a very good job. I'd be there, right? That's 2 radians. And then 3 radians would be over here somewhere. Do y'all agree? And then so I wonder how many radians there are. Yeah, thank you. I wonder how many radians there are in a full revolution. How many of them do you think there are in half a revolution, in 180 degrees? So if I draw my x and y axes like this, here's my x, here's my y. If you believe my drawing is pretty accurate, do you think there's more than 4 or less than 4 radians in a half rotation?
There's 4 radians and a half.
So this is 1 radian. This is not a very good 2 radians. Right? 3 radians. Less than 4. It does turn out to be less than 4. It's smaller than 4. Is it more than 3?
Yes.
Okay. So if I go and I rotate, I want you all to understand this. If I go like this, which is 180 degrees, do you agree that that's equal to some number of radians? And you're telling me that that number is between 3 and 4, just visually, if you're buying what I'm putting up here.
Yeah.
Somewhere between 3 and 4. That's what it is. Do you want to know exactly how many it is? 3.1415. Oh wait, that number pi. That's what it is. It's exactly pi radians.
It is exactly the length of the string right now. If you took that length of that string and you stretched it out exactly how many times at 3.14, it would complete the entire circumference of the circle, correct?
Say that one more time. If I take this string and I measure out 3.14 feet.
One of the continuous planes
Mm-hmm.
in the 3.14, doesn't it create the complete circle in 3 revolutions or something like that? I'm trying to figure out how it's explained before.
Okay. I'm not sure how it was explained. I was trying to follow. I thought you wanted me to measure this 3.14 and then, okay, sorry.
It was the way you were explaining the angle of the circle.
Okay.
Using the length of the string to relate to the length
this 1 radian comes from the idea that this length right here is equal to this length right here. And regardless of the circle size, this length are the same. You're forced to draw this angle. There's no other way to do it. And since there's no other way to do it, we have a very special name for it. It's 1 radian. Now, the thing is, degrees and radians, they aren't married to each other in the sense of like, okay, you have to have nice numbers. The reason why degrees were so nice was because we said, okay, let's take a full rotation, cut it into 360 pieces, everything's beautiful. And then we said, wait a minute, look, if you do this cool little property, you get this angle here. No matter how you do it, you always get this angle. Now after that, we asked ourselves, how many of these fit into a circle? And it turns out that if you want to get 180 degrees, you're not going to do one of these, you're not going to do two of these, you're going to go a little bit past 3. In fact, you're going to go 3.1415. You're going to go to an irrational number. It's pi. So 180 degrees is equal to pi radians. Do y'all see it or not? I mean, this is a pretty important thing. It's like this angle measure right here, right there. That's 1 radian. There's 2 of them. There's 3 of them, and then 0.1415. There's a little bit left over. My drawing sucks, but it's 1, 2, 3, and then the little remainder is the 0.1415. Yes?
The stuff we did earlier, right,
Mhm.
with the angles,
Yes.
common angles,
Uh-huh.
is that where this comes into play?
Yep, we're about to do that. Yep, I'm about to start counting around in a second. All right, so if a half rotation is pi radians, then what's a full rotation? 2 pi radians. So 360 degrees is 2 pi radians. Now, I'll start putting rads or just rad. I might just put rad or rads for radians. And this is a very important thing to note, that if I did not put rad and I wrote 360 degrees equals 2 pi without the rad, it would be correct. If you do not put the radians after your number, it's understood that you're talking about radians, if you're talking about an angle. However, if you write down 2 pi degrees, these are not the same thing. This is a number of degrees. This is how many degrees there are. This right here is totally different measurement. I'll illustrate this more as we move on in the course. The main key is this. If you're talking about degrees, you better put the degree symbol. If you're talking about radians, put rad, but if you don't, it's okay. All right, let's try and draw this circle again with the common angles. I hate restating what I've already said, okay? Because I'm not trying to treat you all like you're stupid or anything like that. But I want really to emphasize, degrees come from drawing a circle and cutting it up into equal pieces. Radians comes from this very cool property that if you go out, walk across, that always gives you the same angle no matter what. And then we use that and then say, okay, fit it into the circle, and we get these weird, just doesn't work out nice for us. There's pi radians in a half rotation, and there's 2 pi radians in a full rotation. All right, common angles. Now, in our viewing of the common angles in degrees, the first thing we did was we just went around to the corners first, right? So let's try that first. This will be 0 radians, won't it? Now, I'm not going to put rad. I'm just going to put 0 radians. How many radians was this? 180 degrees.
Pi?
This was pi radians, right? So what about 90 degrees? That's half of pi, isn't it? If this whole thing is pi, then this would be half of it. Now we can write that pi over 2, or you can write that 1/2 pi. It doesn't matter. Either way. I prefer this, but in calculus, we probably do this. All right. Now, what about this one right here? This one. 3/4 pi?
2 pi over 2?
What's that?
2 pi over 2?
Not 2 pi over 2. 3 pi over 2, right? Okay, so this is, okay, remember how I said you're going to count around? Do you agree that jumping from here to here to here to here to here is always the same jump? Yes? So I rotate by a certain amount, then I rotate by a certain amount, same amount, every time. I would like us to count our way around here. All right? This right here is a rotation by pi over 2. Yes? Then I do a second rotation of pi over 2. So this angle here should be 2 pi over 2. Yes? I'm going to write that down. 2 pi over 2. But what happens to the 2's? They cancel, so that's just pi, isn't it? So now I'm going to rotate again by pi over 2. So this is, how many times have I done this now? This is my third rotation of pi over 2. So this should be 3 times pi over 2. So this is just going to be 3 pi over 2. You understand how I'm counting here? Okay, and then I'm going to rotate one more time by pi over 2, and I'm going to get 4 pi over 2. But 4 pi over 2, if you reduce this, this is 2 pi. Okay? Understand how I did that? To me, this is much easier than trying to memorize all these, all right? If you just count your way around. What was the next thing we did after we got the corners on the degrees?
45.
We did the 45s. Let's do the 45s here. So our 45s go like this, 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 and this. Now we have to know what this first one is. If this was pi, right? If this was pi, and I'm only going to go this far, that means I've cut it into 4 equal pieces. It should just be pi over 4 or 1/4 pi, or pi fourths, however you want to say it. I'm going to write this as pi over 4. That's one of them, right? What's the next one? 2 pi over 4, right here. Now you don't need to write this down, but I just want you to see how this matches up. This is 2 pi over 4s. And if you reduce that fraction, you get this, don't you? Okay, so we're here. Next one, 3 pi over 4s. So I put 3 pi over 4, and that fraction does not reduce, right? 3 pi over 4 doesn't reduce. So we go another 45 degrees. Now we're at 4 pi over 4. The 4's cancel, we just have pi. Next one, 5 pi over 4. Next one, 6 pi over 4. Does everyone see 6 pi over 4 would reduce to be 3 pi over 2? Okay. Next one, 7 pi over 4. And then finally, 8 pi over 4, which would be 2 pi. They would reduce. After the 45s, we did the 30s, right? 30, 60, 90 went around. So let's do that again. It's going to be here, 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 here. All right. So let's try and get the measurement on this one. And you have to just kind of erase from your mind the black in here. Just look at the red. So pi was all the way, right? This was from here to here. We cut it into 1, 2, 3, 4, 5, well, 6 pieces, right? 3, 4, 5, 6, sorry. I forgot. It comes up here also. All right? So if we cut it into 6 pieces, then this first one should be pi over 6. And now you start counting. Here's pi over 6. Now here, 2 pi is over 6, right? 2 pi is over, which will reduce to pi over 3, right? So this is going to be pi over 3, but that's really because it's 2 pi's over 6. And now we count again, and this is going to take us vertical. How many of them do we have? 3 pi over 6, and then that's just pi over 2 because the fractions reduce. Next one, 4 pi over 6, right? But that reduces. 2/3 pi? 2 pi over 3? Are y'all following what I'm doing here? I know some of you are, but I just want to make sure everyone is, because Most of the time when this is introduced in pre-cal, it's just like, here are the common angles, kind of memorize them. The counting out, I think, makes your life a lot easier later. Eventually you won't have to count it out, but for the time being. 2 pi over 3. Next one. Where are we at? I lost my place. 1, 2, 3, 4. I'm at the 5th one, right? So this is going to be 5 pi over 6. And then we get all the way across, 6 pi over 6. That's pi. Next one, 7 pi over 6. 8 pi over 6 is the next one, and I believe that reduces, right? 4 pi over 3. Next one, we're at 9 pi over 6 right here. I'm just gonna illustrate this. This is really 9 pi over 6 for us, and when you reduce that out, you get this, 3 pi over 2. Now, 10 pi over 6. 5 pi over 3. 11 pi over 6. And finally, we get to the last one, 12 pi over 6, which is 2 pi.
These are 12ths, right?
Pardon me?
This is 12ths.
Twelfths? Yeah, it's funny that you say that because I was exactly just thinking that as I was doing this. It would be really, really nice if we just started blank slate, and just cut everything into twelfths. Because do you agree that well, if you look at all the denominators that we have in all these fractions, we've got 2, 3, 4, and 6, right? If you could come up with a common multiple of all of those, then that would account for all of these. So if you look at, 12 is a multiple of 2, 3, 4, and 6. So if you cut it into twelfths, this would work. But you would also get more angles in here that aren't here. Like you would have, this would be pi over 12 right here. And then you'd have 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi. So you'd have a bunch of angles that aren't common, but that would be an efficient way. In fact, when I write programs, I'll show you all stuff that I'm doing, like visual stuff later. Whenever I write programs to show something geometrically with circles and stuff, I always have my increments jump by pi over 12 so that I can jump to all the common angles as I animate things. That's kind of cool that you thought about that. All right. Those are all our common angles. I hope that you feel okay marching around on a circle. Now it's just a matter of you getting your hands dirty, messing around with it. All right. Let's do our first theorem. Now, do y'all know what a theorem is? It's something that's been proven, all right? So the idea would be something like, in mathematics, what we have are what we call our axioms. Those are the things that we say, like, this is the definition. We say, we define a number to be something. We set up these axioms, and then from that, we try and prove things are true based on those axioms. So this is something that has been proven. If you take a vertex and you extend a ray, but you stop it, so it becomes a line segment, and this has a radius of r, so distance from here to here, r. And then you rotate, right? Rotate this through some angle. So imagine this rotates through some angle theta. Then the measurement of this right here, which we will call S,